Alrighty then.
So today we are going to continue. Oh, I forgot what chapter number this is. I'm great at this. We're going to continue chapter number, whatever number this is, the second one after the last exam, where we're going to go further into the craziness that is relativity. So far, we've been talking about 29, chapter 29. That's what number it is. So far, we've been talking about special relativity, the idea that time and distance is relative depending on how fast you're going. Um, Sorry, with a picture of Doctor Who on the screen and then me saying about to say time and space, I started like TOTUS in my mind. So where we left off is we had explained an equation to explain how length changes with time. But I'd yet to do an example problem. So we're going to jump right in with an example problem. So here we go. This is not one I wrote. This is a textbook problem, but it works. An observer on Earth sees a spaceship at an altitude of 4,350 kilometers moving downward towards Earth at a speed of 0.97 c. What is the distance from the spaceship to Earth as measured by the spaceship's captain? See, what I can say here is whoever's stationary, that is the proper distance. And if someone on the Earth will consider the stationary person, they say the distance is 4,350 kilometers, that means that is the proper distance. Once again, different from time, where the proper time is the person moving. We know the velocity of the ship. We want to know how far the person on the ship thinks it is. That'll be L as opposed to L proper. And I can just say the distance is the proper length over gamma, which means the distance is the proper length times the square root of 1 minus v squared over c squared. Now, like always, I'm not going to bother solving for c more than that, or v. I'm sorry, I'm not going to bother solving for v more than that. I'm going to just plug it in as c and say it'll be the proper distance, square root of 1 minus 0.97 c squared over c squared. 0.97 squared is 0.9409. My c's cancel out. I can subtract, I can square root, and I can get the answer. And so the person on the ground says they're 4,000 kilometers away, but the person on the ship thinks they're only 1,000 kilometers away. The distance is different. There is a part B on this problem. Part B says, after firing the engines, the captain measures her ship's altitude as 627 kilometers, with the observer on Earth measured to be 625 kilometers. What's the new speed of the ship? Well, the person not moving sees 625. That's the proper length. The person moving says 627. That's the length. And now we want to solve for V. If you want to solve for V instead of the other way, like we just did, it just takes a bit of algebraic rearranging. See, what I could do is I can divide both sides by proper length, and then I will square both sides. By squaring both sides, I can get rid of my square root. Now, what I did here is I kind of did both things in both steps, but I added v squared over c squared to both sides, and I subtracted L minus LP squared from both sides to rearrange as follows. If I want to solve for v, I can square root both sides and multiply both sides by c, and I can get an equation for the velocity. It's just going to be c times the square root of 1 minus L squared over LP squared. 267 over 625 is this number, which I can square and subtract and square root, and I get them now moving at 0.904 c. Wait, what were they going before? I can't remember. They were going at 0.97 c before. And that's the logic. It kind of is plug and chug. The hardest parts of these problems is keeping track of which one is proper length, which one is proper time. That's the trick. Well, once again, how I recommend it, not how it is, proper length is the frame of the object, and is the length of the object when at rest. Proper time is the frame of the moving person. That's the setup. Proper length is the thing at rest. Proper time is the moving person. Any questions?
No?
Only you today. Now earlier I did that problem with whatchamacallit, Mickey Mouse. Um, I have a lot of fond memories of when I learned this stuff in undergrad, mostly because my teacher was crazy. And so a lot of the example problems we're doing are ones that I just remember being asked and being confused by. Um, this next one is one of them. Although I don't think you use Quicksilver, but I'm going to use Quicksilver because I'm me, comics. So, Quicksilver from the X-Men and or Avengers can run really, really fast. Let's say he is holding a 5-meter long ladder, and he's holding it parallel to the ground. He then gets up a good sprint, eventually reaching 98% the speed of light. How long is the ladder according to Quicksilver once he is running, and according to his sister, the Scarlet Witch, who is standing on the ground as Quicksilver goes by? And I lied. This wasn't the problem I thought it was. The problem I thought it was a ladder twice as long as the bone, and how fast you have to go to get it to fit in the bone, which is a weird problem, but it exists. So let's look at this. At rest, this ladder is 5 meters long. If it's 5 meters long at rest, that is how long it is in Quicksilver's reference frame. It's 5 meters long to him there. It's 5 meters long everywhere. That is the proper length. Now, this seems weird because I've been saying that the proper length is the reference frame of the thing to the people not moving. That's because most of the time, the object you're changing the length of isn't also moving. See, if I look at the last problem, the proper length with the distance between the spaceship and the Earth isn't moving. That's why that was the proper. If Quicksilver is holding the ladder, him holding it is the proper. And that's the general idea. Going back to what I had just said before, this slide, proper length is in the frame as the object. And it is the length of the object when it is at rest. So for this one, frame of reference of the object when it's at rest, that's the distance from the Earth to the spaceship at rest. This one, when it's at rest, the thing was 5 meters at rest and in the frame. So LP will be what Quicksilver sees. It's his sister who will see something different and will see a new length, which I can plug in for and go and solve. And she'll see it less than a meter long. This is the hard thing about this chapter. Time is kind of simple because time is just proper time is the moving thing. But proper length, as we just saw here, might be the moving thing, might not be the moving thing. Proper length is the length at rest. And if the object is moving, then it's what the person moving sees. If the observer is moving and the object is not, then it's the stationary length. That's the difference.
So you're telling me that if he was running that fast past her, he could carry that 5 meter long ladder through a 1 meter long doorway?
Yeah.
That's greasy.
Yep.
That's
Length is
wild.
relative. Now, for the next bit of mind-bending Einstein theories, which, as I said, these have all been proven too, I want to go back to the beginning, where we said the speed of light is the same in every reference frame. So let's go back to just talking about reference frames where we started. If someone, I like this sled picture, so I'm going to use it. Let's say this little girl can throw a snowball at 1.5 meters per second. If she's being pulled at 1 meters per second, an observer would see it at 2.5 meters per second. If she throws it behind her at 1.5 meters per second, while being pulled at 1 meter per second, an observer would see it at negative 0.5 meters per second. That's just classic addition of vectors. Now, I'm going to start using a notation here that's going to come up a lot in the next few slides, so I just want to explain it. What we're going to say is u is the speed as seen from the stationary reference frame. U prime is the speed as seen from the moving reference frame. And v is the velocity of the reference frame, which I don't think I actually wrote there. Oh, it's at the top one. V is the speed of the reference frame. Oh, that's FOR for frame of reference. But one of the things we started this chapter with is that light travels the same speed at all reference frames. And so that means if instead of a snowball, this girl was flinging light, we're getting no dazzler up in here, this all breaks down. We can't just add them. And therefore, since speed moves at the same speed at all reference frames, since light moves at the same speed at all reference frames, we need a different way to add vectors for when we approach the speed of light. To explain why, that in this case, both u and u prime will be c. U prime being how fast this guy thinks it goes, u being how fast she thinks it goes. That they both have to see that c, and if u and u prime is c, for the equation we already have, that only works if v equals 0. But I'm telling you, v can be any goddamn speed and it works at relativistic speeds. And so we have a new equation to add vectors. Anytime you need to add two vectors and you have relativistic speeds, you can't just add them. Now, I'm not talking about vectors like one this way, Pythagorean theorem stuff. I mean adding two vectors pointing in the exact same direction or opposite. We're ignoring a 90-degree shift right now, or any angle shift. If two vectors are pointing in the same direction, or two vectors are pointing exactly opposite direction, how to add them will be more complicated at relativistic speeds because of this light moving the same at all reference frames. And this is the equation. If a stationary observer sees someone moving at velocity v, throw an object at a velocity u prime, the observed speed goes by this equation. Once again, u is the speed according to someone stationary. U prime is the speed according to the person moving, and v is the speed of the person moving. Now, you can rearrange this equation and solve for u prime. It's not impossible to do, but it's cumbersome. I'm not going to make you do it. Here's the equation if you want to go the other way. Also, watch your signs. If someone throws u and v are in the same direction, make them all positive. But if u and v are in opposite directions, you're still going to have to make one negative with respect to the other. So let's make sure this works before we go through a problem. And how we're going to make sure it works. Let's do this problem right here. That this person, I'm just going to italicize that S real fast. Let's say the person at S prime sees the light moving at C. And so let's see what the speed this person sees, what the speed U is. Well, if the person at S prime, if the moving person sees light move at C, we know U prime must be C, U must be C, because C is the same in all reference frames. So that's what we're going to check. I'm going to plug in U prime as C. This bottom bit will reduce. I'm going to factor a C out of the top, because this C plus V, that's the same as C times 1 over 1 plus V over C, which is C. It works. Now, for non-relativistic speeds, it still works, because for non-relativistic speeds, U plus U times V will be much, 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 much smaller than C. And therefore, for non-relativistic speeds, this is going to be approximately 0. And if that's approximately 0, u will equal u prime plus v. Oh, that's a horrible u, and a u prime plus v over 1. So it'll work at non-relativistic speeds. There's just no need to do it at non-relativistic speeds. Okay, let's do an example problem. This is another one from that old teacher who literally had an exam involving Star Trek that the Enterprise was moving at 0.9 warp, and I didn't know what speed warp was, and he refused to tell me. Told me that should be common knowledge and I should know that information, and I failed an exam problem because of it. So anytime you think I'm being an ass, I could be worse. Side note: warp 1 is the speed of light. I have since know that because of that teacher. So suppose the USS Enterprise is traveling at 0.5 C relative to an at-rest energy. I guess it is proper English. Relative to an at-rest enemy ship. The Enterprise fires a phaser that moves at 0.9 C relative to the Enterprise. How fast does it appear to the targets of the attack that the phaser is incoming? So this is what I got. I got the ship is moving at some speed. The speed the ship is moving, that's v. The Enterprise fires the phaser, and we say it's moving at 0.9 C relative to the Enterprise. That means that is u prime. What these people over here think, that's a Klingon bird of prey, the speed they see it coming, that'll be u. And that's what we want to solve for. And so I'll say, the ship moves at 0.5 C. They fire the phaser at 0.9 C. Now, classically, we would say that the enemy ship, classically we'd say they would see it coming at 1.4 C. But we know that's wrong because nothing can move faster than the speed of light. But using relativity, we can figure out how fast it comes. Because how fast they see it approaching, that will be u. And so I'll say the speed they see it approach will be u prime plus v, 1 plus u prime times v over c squared. Now, 0.5 c times 0.9 c is 0.45 c squared. That lets me cancel out my c squareds to get 1 plus 0.45 or 1.45. And 1.4 divided by 1.45 is 0.966 c. And so that's how fast this enemy would see the thing approaching them. Slightly faster than the Enterprise saw it leave, but not nearly as fast as classic physics would make you think. Okay? Now, I said before, the hardest thing in the earlier problems was knowing which is proper time, which is proper length, and so on. The hardest things on these, keeping track of what's u prime, and what's v. Especially if you have handwriting like mine where your u's and v's will sometimes look like each other. That's the tricky part. Once you get that, it's plug and chug. So anything prime is the moving reference frame. U is the stationary reference frame. V is the actual movement of the frame of reference. Okay. Let's do one last one. Suppose the Milano, which is Star-Lord spacecraft in Guardians of the Galaxy, is traveling at 0.6 C in the positive x direction, as measured by a nearby Xandar base observer at rest. So that is traveling at 0.6 C according to someone at rest. So that's either going to be U or V. I'm not sure which yet. While Rocket Raccoon is traveling his own vehicle directly toward the Milano in the negative x direction. So what I got is this ship here. Oops, that's not what I meant to tool I meant to use. Kind of like that. Is traveling this way at 0.6 C. And Rocket Raccoon in some other ship, I'm just going to make it something round, is traveling the opposite direction at negative 0.8 c. Now, and that's both are relative to someone on the ground. What's the velocity of the Milano according to Rocket? Well, that means we want Rocket to be what we're looking at. That means we care what Rocket thinks. That means that 0.8 c, that is the frame of reference we're going to work in. If we want to find, the mouse keeps not showing up. If we want to say, if we want Rocket to be the frame of reference we're solving for, this is V. And now before I read that last sentence, I didn't know which one was V and which one was U. But that's V because that's the frame of reference we are flipping into, because we want according to him. This 0.6 c, that's relative to someone on the ground. So that's the speed relative to someone on the ground. And so we can say the new frame of reference is negative 0.8 c. The actual speed, according to someone on the ground, that's the 0.6 c. We want to know the speed Rocket Raccoon sees. That is the speed according to someone in a moving frame of reference. And the speed according to someone in a moving frame of reference, that is going to be u prime. So we get our equation. Once again, the hardest part is this part. But I can plug in. 0.6 c times negative 0.8 c is negative 0.48 c squared. My c squareds cancel. I can add that 1 in, divide. Now this is kind of crazy because if you are in a car driving 20 miles per hour and a truck is approaching you at 30, let's just actually use these numbers. If you're in a car moving 60 miles per hour and a truck is approaching you at 80 miles per hour, to you it'll look like 140 miles per hour. You just add them up. But that doesn't work here because of relativity. Now, that is basically the end of general relativity. I got a little more general relativity. Not much though. But before we continue on to the next topic, I want to go through something batshit crazy about this that is kind of interesting as a thought experiment. I will admit I did not do these calculations. This is all from the book called How To by Randall Munroe. He's the creator of XKCD, which is the guy who makes all the stick figure comics I always keep putting in my slides. Like, I think there was even one in this chapter. This is from him. That's a problem. This is from him. This is from him. I highly recommend his webcomic and his site in general. But he did a problem about someone traveling on a magical space scooter. It makes sense in the problem. And says, what happens if you leave the Earth accelerating at a rate g? Just what happens if you accelerate for g instead of just free fall on Earth, like I just dropped this, it falls, but you just keep going out at space at that rate? What would happen if the spaceship accelerated away from Earth at 9.8 meters per second without relativity? Without relativity, if you accelerate 9.8, you would hit the speed of light and pass it within a year. Now, we know this can't happen according to relativity. So let's talk about what happens instead. If you use relativity with the addition of vectors, because basically it would involve using relativity adding acceleration times time plus velocity, what you'd have is at 1 year of travel, you would be traveling at about 0.75 c. And at 1 year of travel, you have only traveled a year, but everyone observing you has said you've been traveling for 1 year, 2 months. After 2 years of travel, you would have traveled, um, you would say you traveled further than a, you would say you traveled, you'd be going at, yeah. You would say you've traveled further than 2 light years. Oh, sorry. Someone stationary would say you traveled more than 2 light years. The reason why is because contraction. You won't be traveling faster than the speed of light. Um, it seems like you'd be going faster than the speed of light because you traveled more than 2 light years in 2 years. But the reason why is because for you, you didn't travel 2 light years. Only the people observing you thinks you traveled 2 light years. Because for you, space got smaller. You traveled a further distance because you shrunk space. This is one of the theories on how to do space travel at farthest distances. If we can accelerate fast enough, we can shrink space. If you traveled 3 years, the entire time accelerating at 9.8, never changing your acceleration, after 3 years of traveling, you would have traveled 10 light years. And someone outside the ship watching you would say 10 years passed. And that's how it happened. You claim someone watching you says you traveled 10 light years for just about 10 years. Not quite, because you're not actually going the speed of light. But for you, it's only been 3 years. At 4 years of accelerating at that rate, 30 years would have passed for someone watching you. 5 years, someone watching you would have said 80 years passed. And at 10 years, someone watching you would have said 15,000 light years passed. You would be halfway to the center of the galaxy. And if you do this for 20 years, your time, you sit in the ship for 20 years, probably bored out of your fucking mind. If you accelerate at G for 20 years, your time, for everyone else, it would be about 1 billion of years per your year. That you're from between your 20th year and your 21st year, 1 billion years take place for everyone else. And here's the thing. You wouldn't reach the edge of the galaxy. Now, this seems crazy, that if you traveled 1 billion light years, you should probably reach the end of the galaxy. The edge of the galaxy is actually closer than 1 billion light years away. But the galaxy is constantly expanding. And even though you've traveled, in your frame of reference, about 20 light years, in the galaxy's frame of reference, about 1 billion light years, but even at this rate, the edge of the observable universe would still be expanding faster than you are going. And even though you're moving at almost the speed of light, and it's only been 20 years for you, but you've gone this many light years, because for the rest of the world, billions of years have passed, the edge of the galaxy has moved away from you faster than you're going. What is called the cosmological event horizon is how far we can possibly get if moving at the speed of light. And anything past the cosmological event horizon, we can never reach, because even moving at the speed of light, we would never catch up to it, because it's so far away that it would have moved just out of reach by the time we got there. Okay?
How fast would we have to move to reach the edge of the observable universe?
We can't. We'd have to move faster than the speed of light. It's not possible.
Wild.
Now, this is where Einstein went a little crazier with it. And this next bit is actually part of a different publication, where he's like, you know what? Velocity change, time changes in different reference frames, and v changes in different reference frames. Therefore, velocity must be all fucked up too. And we know momentum. Momentum's mass times velocity. We use it for conservation of momentum. And conservation of momentum usually assumes the mass of the object is the same everywhere. Conservation of mass. The mass of an object can't change. I'm going to call m naught, m sub 0, as the mass at rest. That if I weigh something and say it has a mass of 2 kilograms, that's its mass when it's sitting still. That's going to be important in a second. But when you hit relativistic speeds, your momentum can no longer follow that equation. That the definition of momentum being mv needs to be shifted for relativistic speeds. And mv will be gamma mv. Once again, I'm using m naught here for mass at rest. Likewise, the kinetic energy equation will change. That the kinetic energy of everything will include gamma at high velocities. Well, kinetic energy is usually 1/2 mv squared. But the kinetic energy at the speed of light, and that right there is the speed of light, not at and near the speed of light, gamma, because gamma depends on v, that the kinetic energy of something at near the speed of light will be gamma m naught c squared minus m naught c squared. Well, gamma is going to include our velocity. Now, once again, if you try to put in non-relativistic numbers, this works. And in this equation, it gives the kinetic energy as a function of your velocity at relativistic times. This last term, m naught c squared, that is called the rest energy. It has no effect on how fast you're going. It's just this factor of energy due to what you have not moving. But this is kinetic energy. What it ends up being is this rest energy, the energy of not moving. That's what we used to call potential energy, right? Potential energy was the energy when something wasn't moving. And therefore, this m naught c squared, we can kind of say is kind of like the potential energy. And if I add it to both sides, I can say the total energy is gamma m naught c squared. That the total energy something has will be its kinetic energy plus the potential energy, which would be the same as m naught c squared over the square root of 1 minus v squared over c squared. And what Einstein said is any object moving will have a total energy of gamma m naught c squared. Now, this may seem weird to you because if there's anything you know about Einstein, you know E equals mc squared. Everyone knows E equals mc squared. No one has any fucking idea what it means for the most part, except you're about to learn, but everyone here is E equals mc squared. The thing is, E only equals mc squared because Einstein did some crazy math here. E does not equal mc squared in the normal sense. E equals gamma mc squared. That the energy of something is gamma, the same gamma we've been using all chapter, times the mass at rest, c squared. However, Einstein decided to shorthand it. And he said we would talk about a relativistic mass. That if something is moving at a high speed, we could say it's as if it had a new mass. Its new mass being gamma m naught. And therefore, if mass is gamma m naught, E equals mc squared. Now, in this class, I'm never going to use the equation like that because m is not mass here. And you probably learned whenever someone told you E equals mc squared, they probably even said it was mass times speed of light squared. But m isn't mass in this equation. M is relativistic mass. M is not how much mass something has, but a adapted version using gamma. And this will be true for all objects. If you heat something up, it'll have more internal energy. It actually has more mass. If you take a spring and stretch it, it suddenly has more mass. Now, this goes crazy because the law of conservation of mass is one of the fundamental laws. All of chemistry is based off of it. But what Einstein said here is that the law of conservation of mass doesn't really exist. It's the law of conservation of energy. And seriously, this spring like this, weighs less than this. Not by much, but by a little bit. And that all objects will have an energy of E equals gamma m naught c squared. Be careful using mc squared, because once again, in E equals mc squared, m is not mass. Okay? Crazy side note before I continue this, just because I think this is nuts. I just want to give you a timeline here. In 1905, Einstein said light is a particle and that photons exist. And the photoelectric effect, which we covered the photoelectric effect in passing, but the whole idea that light is a particle, he published that in 1905. Special relativity, aka everything we did up to that E equals mc squared shit, all the vector addition and light and time changing, he published in September of 1905. E equals mc squared and all this, he published in November of 1905. There was also a publication in July 1905, because I don't want you to think he was being lazy or something, but that's about a whole other topic. All of these ideas all came out the same year and fundamentally changed how we looked at the world, which is why people reveal Einstein the way they do.
Big year.
Yeah. I don't remember what year general relativity came out, since we're going to start that soon. I think it might have been 1906, though. I think he rested during December. Now, going back to these equations. That means the energy of any particle is gamma m naught c squared, and the momentum of any particle is gamma m naught v. These two equations can kind of be put together. If I take my energy equation and square both sides, and also take my momentum equation and square both sides, and then I'm going to take my momentum equation and multiply both sides by c squared, and I can say energy squared minus momentum c squared equals this mess. On this mess, I'm going to factor out a c squared. So I'm going to factor out, I lied. I'm going to factor out a gamma squared m naught squared c squared. Don't forget we have an equation for gamma, which means this is gamma squared. If I multiply this whole thing by c squared over c squared, that is the same as this. I'm going to plug that in for gamma squared, which is this mess. But in all of this mess, this can cancel with this. And I get the following equation. This equation is kind of interesting. This equation says for any particle, the energy squared equals the momentum squared, c squared, plus the rest mass squared, c to the fourth. And the reason this is important is because momentum is mv in the normal sense, and in the relativistic sense, it's gamma mv, right? Something can only have momentum if it has mass, right? Momentum's mv or gamma mv. If m equals 0, momentum must be 0. However, with this equation, Einstein had the idea that photons had no mass. And he said if they have no mass, if m is 0, then E squared equals P squared C squared, or E equals PC. Now, yes, momentum depends on mass. Shouldn't that matter? But Einstein went the opposite way. And he said if something has energy, it therefore must have momentum. And if something has no mass, it can still have momentum. And this is how we were able to work out the energy and momentum of photons. That for any photon, we can say how much energy it has, even though it has no mass. Just so you know, these numbers are sometimes put in electron volts. Electron volts is a different unit of energy. Oh shit, I'm a little short on time. Hopefully I'll get to finish the fun bit. Okay. Let's do an example problem. Let's say an electron is moving at 0.85 C. What's its total energy and kinetic energy? And compare it to classical. Well, total energy is gamma m naught C squared, or kinetic energy plus m naught C squared, where this is gamma. If I'm going to do this for an electron, I need the mass of an electron, and that's it. There's the mass of an electron. I'd have to give you that. If I want to find the total energy, it'll be m naught C squared over gamma. And I'll just plug in m naught C squared gamma. I did 0.85 C. I got to square that number. Cancel out my C's. Subtract. Square root. And that's how much energy the photon has. As for kinetic energy is that minus m naught C squared. Which m naught C squared, I'm not going to bother solving for it again, because m naught C squared was the top of this fraction. And so that's the kinetic energy. Now, classical physics says the energy is 1/2 mv squared. And if I plug in just 1/2 mv squared, I get this number. I get a fraction of the energy. Because energy is going to change at relativistic speeds, because your mass, your apparent mass, would change at high speeds. So at high speeds, your time changes, your length changes, and your mass changes. Okay. Now, I only got 8 minutes left. I'm gonna go a little crazy with the time I have left. This was special relativity. Special relativity was what happens if there was an inertial reference frame, that the reference frame is moving at near the speed of light, but is not accelerating. Einstein wasn't happy with this. He said he wanted something that could explain an accelerating frame of reference. His reason was mass determines inertia and the strength of a gravitational field. And this bothered him. He said that mass shouldn't be the same in both, since mass can be affected. That really there should be two different types of mass. Mass that affects inertia, mi, and mass that affects gravity, mg. Now, in the equation to solve for the force of gravity, this guy right here, capital G is defined so that they are the same. But they're mostly the same anyways. And Einstein thought that seemed like a coincidence, that what affected gravity was the same that affected inertia. And he thought it was a really weird coincidence. And he made the following thought experiment. Let's say someone's at rest on Earth. They feel the force of gravity, right? Let's say we take someone else, we put them in no gravity, and we put them in a sealed box that accelerates upwards at 9.81 meters per second squared. When he says that if you were in that box, you would not be able to tell the difference. That if you were in the box, it was accelerating uniformly. Things would accelerate away from you, drop exactly the same. One, the object would be falling away from you. The other, the object would be staying still, and you'd be moving away from it. But you wouldn't be able to tell the difference between the two. And he proposed no experiment would ever be able to tell the difference between these two cases. This has a really weird side effect, though. Because if that's true, let's say you're in an elevator accelerating upwards at a rate g, and you shined a light. The photons would come out in a straight line. And if you're accelerating upwards, it'll look like the photons bend downwards. Not because the photons are, but because as the photon comes out, you moved up past it. That this would move nice straight across, but as it moves straight across, if you move up, it'll look like it went below you. But since being in a moving elevator accelerating at g is identical to being on Earth, that means that this must also happen due to gravity. And this means gravity must attract light. But photons have no mass. And the only equation we have for gravity depends on mass. And if photons have no mass, and if gravity affects light, that means we must have gravity wrong. That our fundamental understanding of gravity must be off. Because gravity can attract things without mass. And he postulated two things to explain this. The first, all laws of physics are true in all frames of reference, including accelerating ones. And at a point, the gravitational field is the same in an accelerated frame of reference with no gravity. Just like that's what I've been saying here. And if this is true, if accelerating is the same as being in gravity, that means mi and mg, the inertial mass and the gravitational mass, really are the same. And this was published 2 years after. I thought it was a year after, but it was 2 years after. And this has weird effects. Because if gravity and acceleration treated the same thing, we know time and length can be distorted by velocity, and acceleration leads to velocity. That means if acceleration can distort time and length, that means gravity can distort time and length. And this has been proven. Time will change depending on gravity. Time will change depending how fast you're going, but time will also change depending how strong gravity is. This goes to the movie Interstellar if you've seen it. That's like the whole thing with gravity, time is different for everyone. It's a real thing. It's been proven. Rays of light near the sun have a lower frequency because time is different near the sun. And how Einstein explained this was the curvature of space-time. What he said is gravitational force does not exist. That equation, F equals G m1 m2 over r squared, it's wrong. It's a good approximation. You can use it, but it's wrong. And he said what it is instead is that all objects exist in space-time. And space-time is a way to talk, it's a fourth dimensional thing. It's past third dimension. It's hard to picture. But what he said is all objects exist in space-time, and anything with gravity will distort space-time. And all objects will move in straight lines following the curvature of space-time. Now, this is a really weird idea, and it's very hard to visualize. The best way to visualize it, and I am so close to running out of time, but I'm going to try to make this work, is what is commonly referred to as the rubble sheet explanation. That this is space-time. If you put something heavy in it, space-time gets warped. And if you go and you put like something else in space-time, it'll move down into the well. It'll move to a lower point. Come on. You don't need to hear what he's saying. Just want him to drop something. It moves down in. It moves down in because it's moving in a straight line in space-time. And things orbit like this, if you give it a sideways velocity, because it's matching the direction of space-time. That all things, the heavier you make something, the more it warps space-time, the more it'll pull objects in. And that's the idea. And this has been proven. The fact that gravity isn't a force like we have talked about. It is a force, but that G m1 m2 over r squared, all that, no. It's just that space itself is bent and everything moves in a straight line in space towards an area with the bigger pull. This has been proven because during a solar eclipse, one could see a star that is normally directly behind the sun. And the reason why is light from the star bent around the sun, following its location in space-time. And this is the basis of the theory of why black holes exist. That top bit didn't change though, only the bottom bit. It's just different font for some reason. A black hole is saying, theoretically, if we make something with so much mass, it should puncture space-time, making something called a singularity. That is a hole in space-time, leading to something else. And since then, people have proven that black holes exist. Punctures in space-time, holes into it, leading to another place. Also, this warping in space-time, that's why gravity is affected by time. Let's say light is going to travel down these three paths. The yellow one, barely affected by gravity. The orange one, heavily affected by gravity. The green one, somewhere in between. In the presence of a strong gravitational pull, time slows down. Time slows down because the speed of light is always the same. And if these three lines want to get to the bottom of the screen the same distance in x, but really, if space-time is warped, they're traveling different distances. If they're traveling different distances and c is always the same, it must take them a different amount of time to do so. And therefore, time will be affected by gravity. And the warping of space-time will affect everything. Okay? So, I'm sorry I went a minute over. That is the end of that. I'll happily answer other questions afterwards. I'm about to do office hours. But yeah, that's crazy.
Yeah, it's cool stuff.
Next chapter we'll do less crazy, but still Einstein. We'll do practice problems Friday. Have a good day. And seriously, let me know those questions because I might have rushed that last little bit a tiny bit.